All right, we are on day 2 of solving. We're going to do a couple more examples like yesterday where we're trying to solve by square roots just because I never have enough time to do everything in one day that I want to do. So if you want to just pick up in your notebooks exactly where we left off, you could do that, or you can start a brand new page, whatever is easier for you. I'm just going to pick up where we left off. Our goal is still to solve, and we did 6 examples yesterday, so I'm going to call this example number 7 in how to solve by the square root method. So we'll do 3 times x plus 5 squared plus 147 equals f of x. I'm going to put 2 up here at the board at the same time, and you guys are going to work on them. And the 8th example is going to be 3x plus 1 squared minus 36 equals 0. So pause the video, go through, see if you can find x, find the roots in equation number 8, and technically in equation number 7, because there's an f of x there, the slight tweak in vocabulary would be find the zeros of that function. So it's in function notation. Okay, pause, give it a shot, and check your answers. So for number 7, first thing I'm going to do is actually input 0 for f of x to find my 0, to find my x-intercept. Because on the x-axis, the y value is always 0. I'm going to kind of do 2 steps at once real quick because you should begin a little quicker at this. I'm going to subtract the 147 over to the other side and then divide by 3. So if I do that, 147 divided by 3, I'm going to get x plus 5 squared equals negative 49. When you subtract the 147, you will get a negative. Square root both sides. X plus 5 equals plus or minus 7i. So it's an imaginary answer. And subtract over the 5. You then have to decide whether the minus 5 is like terms or not like terms with the 7i. And you should decide because of the I that it's not like terms, so we have to write it in that standard form of negative 5 and then plus or minus 7i. It's still 2 solutions, 2 zeros, 2 imaginary zeros. One would be negative 5 plus 7i, and the other would be negative 5 minus 7i. So 2 imaginary zeros. And then the last one, solving by square roots when it's similar to our vertex form setup, we're going to add over the 36, square root both sides to get 3x plus 1 equals plus or minus 6. And this one's a little trickier because the coefficient of x here is a 3 instead of a 1. So I'm going to suggest, instead of trying to do this mentally, like subtract the 1 and divide by 3 to positive and negative 6, it's probably easier if you set up 2 separate equations. You're less likely to make a mistake. So one equation would be 3x plus 1 equals positive 6, and the other would be 3x plus 1 equals negative 6. You're just separating the plus or minus 6. You could technically do this for all examples. I think it's really only necessary, though, if the coefficient of x wasn't a 1. And if you notice in the parentheses, it was a 3. So over here in the first one, if I subtract the 1, I'm going to get 3x equals 5. And if I divide by 3, my first solution is 5/3, my first root. And the second one, if I subtract the 1, I'll get negative 7. And if I divide by 3, I'll get negative 7/3. So I'm still getting 2 real solutions, 2 real roots there. 1 positive, 1 negative. The negative is not an imaginary answer because that wasn't a negative underneath a square root. Just a negative number. We're going to switch gears a little bit now then and solve a real world problem that involves square root. When we did real world in the beginning of this unit, the focus was more so on the vertex. Okay, there was a lot of vertex problem. Find the highest point. Find the maximum that it jumped. Okay, those words that indicated the vertex, the highest, the lowest, the greatest, the least, the most, the minimum. All those keywords were words that hinted that we were supposed to find the vertex. the problems today and the other examples we're going to do throughout this section are going to be focused on other parts of the quadratic. Will I still make you find the vertex as well? Yes, because I don't want you to forget that skill, and I also want you to be able to distinguish on your own when am I supposed to do vertex and when am I supposed to do something different. That's important as well. So the problems we're going to do today fall into a category called a falling object. Okay, and there's going to be a formula that's going to go along with this. And if you think about an object falling, there's usually a little bit of oomph behind it, or a little bit of, I'm not a physics teacher, so I don't know exactly how to describe this, although I think your long-term sub will do a much better job at explaining this to you because they're in the science field, that when something falls, it's not going to fall linearly, okay? It's going to have, if it's up here, it's going to go woo, and then bam, hit the ground, okay? It's not going to just go straight down to create a linear piece. It's going to create this like half of a parabolic shape. So the formula that we use when an object falls or is dropped, okay, it's not throwing. It'll be different if it's thrown because that has a force or a velocity behind it. Only when an object is dropped or falls. This is the formula. It'll be h of t equals negative, holy cow, calibration. Let me try that again down here. Or let me... negative 16 t squared, crazy, plus h naught. Okay, that's an h sub 0. So in this formula, h of t is the height of the object while it's falling. So maybe the height 1 second later, the height 2 seconds later, the height when it's on the ground. That's the height as it's falling. T is going to be time in seconds. And h naught, that's how it's pronounced, is going to stand for the initial height, meaning the height that it was falling from. So h naught, h sub 0, is your initial height. So this is a formula that does have to be memorized. This is also specific to measurement in terms of feet. If you were to have a different measure of unit or different unit of measure like meters, then it would not be a negative 16. It would be a different value. Meters is technically negative 4.9. So you might see that come up in the future on some examples. But in terms of the formulas you have to memorize, that's the one that you're going to be working with most often. So I'm going to read to you a real-world problem, and I'm going to write down key information. I'm not going to write down everything, just listen to me. So the stuntman is working on the set of a movie, and he's going to fall out of a window that's 100 feet above the ground. Down below, there is a safety cushion that is 26 feet wide by 30 feet long and is 9 feet high. So just some key information here for this example. This guy is going to fall out a 100-foot window. Okay, onto a cushion that has the following dimensions. It is 26 by 30 by 9 feet. Okay, length, width, height. So that's the dimensions of the cushion down below. So the first thing I'm going to do, and we'll always do this in a real-world situation, is come up with our equation first. Before I try to ask you a follow-up question, we need an equation. And I'll refer to that as our model. That's going to be using the h of t falling object formula. He's falling out of a window. So we don't know this h of t. That's his height as he's falling. It's going to equal negative 16 t squared, that never changes, plus the initial height. So how high was the window? Yes, exactly, 100 feet. So that's going to go in for h naught. So this model could be used to now answer any follow-up question, like how long did it take until he was halfway down? So he was 50 feet in the air. Or how many seconds did it take for him to reach a height of 80 feet? Or how many seconds until he reaches the ground? Or vice versa, if it's been 1 second, how high is he? So you can use this model to answer other question. So for part B, I want to know how many seconds until he reaches the cushion. So you do have to think about this real quick, what number you have to sub in and where you sub it into. Because I'm asking for the seconds, we don't know time, so we can't sub anything in for t. What we're going to sub in is a number for h of t. When he reaches the cushion, what would his height be? Okay, pause, think about that. And his height, when he's on the cushion, should be 9 feet high. That was the height of the cushion off the ground. So we're going to set up 9 equals negative 16 t squared plus 100. And this falling object formula does not have a b term. It never will. So we can always solve it by square roots. For real world problems, we do not need to leave anything in radical notation. You can always work with decimals. They make a lot more sense in the real world versus going up to someone and say, oh, it took the square root of 3 seconds to hit the ground. You're not going to do that. You're going to give them an actual number. So if we solve this, I'm going to subtract the 100 over, divide by the negative 16. Like I said, you're going to get a decimal. That's okay. I also don't want you to round this decimal. Okay, the rounding should be saved to the very end of the problem. The sooner you round, the less accurate your final answer will be. So I did not round that number. I wrote the whole thing. And then I square root both sides. And I will get t equals normally a plus or minus sign. But in the real world, a negative time won't make sense. So I'm not going to put my plus or minus sign. I'm just going to go ahead and square root that answer to get approximately 2.385 seconds. Okay, 2.385 seconds. I'm just going to pause real quick. Sorry guys, I had to pause. I had a quick little visitor in the classroom. So we end up with 2.8385 seconds. I'm rounding to the thousandth place just because on the SATs and the PSATs, that's where they have you round to fill in all the boxes on the grid. So just to say in that consistency, I'm going to round to the thousandth place. So it'll take 2.385 seconds until the stuntman hits the cushion. I'm going to ask one more follow-up question about this. We're going to be a little mean for a second. We're going to pretend he falls out the window, misses the cushion, and lands on the ground. But he's only going to break like a foot or something, okay? We're not going to kill the dude. That'd be too cruel. So he's going to miss the cushion and land on the ground. So how long until he hits the ground? Pretending he completely missed the cushion. They put it in the wrong spot. Oops, so hits the ground, not cushion. So for these examples, anytime I ask you, when will it hit the ground, and that's the key word there, you have to know that the height of an object when it's on the ground is 0. It'll always be 0 on the ground. So when I go back to my model, nothing to do with part B, we're going to put 0 in for h of t. So it should be 0 equals negative 16 t squared plus, and our initial height does not change. It's still starting at 100 feet. I'm going to hit pause. You guys are going to go solve this all on your own and check your answer with mine. So if I keep solving, I'm going to subtract the 100. Divide by negative 16. I'm not going to round this answer. We're going to do 100 divided by 16 and write as many digits as we have, which won't be as long as the last one. So 6.25 equals t squared. Square root both sides. And don't put the plus or minus because the negative time won't make sense. And we get a time of 2.5 seconds. That is not rounded. That's just what it ended up being. So it only takes 2.5 seconds until he hits the ground. Not much longer than when he hit the cushion, which was a little over 2.3 seconds. I want to show you one other thing on the graphing calculator. So I'm going to pull that up real quick. This is a little tidbit strategy on how to use the calculator so you don't have to retype in numbers. So in part B of the last example that we did, at one point we had to do 91 divided by 16. And we got that decimal. It was technically negative 91 divided by negative 16, but the two negatives cancel out. Then you had to square root that number. So I could do second x squared, square root's behind there, and then retype that whole number. But another way, if you want to use the answer from above without retyping it, especially if this decimal was even longer, then to do that, you would hit second, then the negative button, because behind the negative button it says answer. That means it's taking the answer from above. So if I hit second negative, that prevents me from having to retype that answer in. And I can just hit enter, and bam, I have that value, okay, that we rounded to then the thousandth place. You can also store numbers in as letters. So if I wanted to use, say, this 2.3848488004 number later on, like a couple steps down the road where I couldn't do the second negative, I could hit STO, which is above the on button at the bottom. So STO down at the bottom. And that's going to store it. Notice it says answer because I'm taking that answer from above as a letter. So I can hit alpha, which is towards the top here. So notice now it's blinking and it has an A for alpha. And then pick any letter of the alphabet. I usually like just to start with A. So underneath that, I'm going to hit the math button because that's where alpha A is. That means anytime I hit alpha A, it's going to use that number. So those are just some cool things about the graphing calculator to help you use numbers that you don't want to round later on in a problem. All right. I'm just going to throw some other examples out at you guys. So if I said you were skydiving and you fell out of an airplane that was 13,000 feet above the ground, how long until you were halfway down? What would you sub in for the first h of t? And what would you sub in for the h naught? Pause and think about that. Okay. The h naught should be the initial height, which would have been 13,000. And the h of t, when you're halfway down, you're at a height of 650, because that's half of 1,300, or sorry, 6,500, not 650. So 6,500 would be the h of t, and 13,000 would be the h naught. And you put those into the formula. So just make sure you understand the difference between h of t and h naught. You'll do some more real-world practice later throughout this section. But we're going to do one last activity or one last example as part of today's lesson that'll lead into tomorrow's lesson. So we're going to go through together and simplify these. Tomorrow we are going to review the quadratic formula, which you learned in Algebra 1. And when you use the quadratic formula, you will get answers at the end that look like these problems. And knowing how to simplify the end of the problem is usually the hardest part for students. So I want to talk about how you simplify the endings of the quadratic formula before we even do the quadratic formula. So looking at the first one, what I would hope you would notice once we practice tomorrow is that there are no radicals anywhere and there is no I anywhere. So when this happens, you're going to combine your numbers until you get two distinct answers. You can do 3 plus 7 over 2 and 3 minus 7 over 2 and get two solutions. Okay? It simplifies down to two exact values. 3 plus 7 will give you 10 over 2, which is 5. There's one answer. And 3 minus 7 is negative 4 over 2, which is negative 2. There's your second answer. So two solutions. And you can do that when there's no radicals and there's no I. Now, a lot of the other problems have radicals or an imaginary component to it. So for those, you have to use that strategy that we talked about earlier in the year, that you can only simplify unless all terms have a common factor. So 6 is a term, 9 radical 3 is a term, and the 12 is a term. So you have to ask yourself, is there a number that goes into 6, 9, and 12? It doesn't have to go into the radical 3. And that number would be 3. So you could divide all the terms by 3. 6 divided by 3 is 2, plus or minus 9 divided by 3 is 3. Radical 3 stays radical 3. You don't touch that one because it's under a radical. Okay? And you've already divided that term by 3. By dividing the 9 by 3, you've already divided that term. And then 12 divided by 3 is 4. This is done. You are not going to do anything further, even with the 2/4. Because, yeah, you might be able to divide 2 and 4 by 2, but you can't divide the 3 by 2. So unless it goes into all of them, you are done. That's as far as you would take that one in terms of leaving it in radical notation. If you wanted to, you could separately divide them by 4, but we're not going to do that. You can leave them like that. Number 3, can't combine them because of the I. So you look at what you can divide all of the terms by. And in this problem, it's only a 2. So we're going to divide them all by 2. And you're done. Okay. Number 4. Is there anything that goes into 10, 5, and 2? No. That's your answer. Can't do anything else with that. Okay? 2 goes into 10, but 2 doesn't go into 5. Therefore, you're not going to simplify that further. Number 5, you have a little bit of work to do first before you try to simplify it, and that's because radical 20 hasn't been broken apart yet. So you can break radical 20 into radical 4 times radical 5, which would become 6 plus or minus 2 radical 5 over 2. And now if you look at each term, they're all divisible by 2. So you'd get 3 plus or minus radical 5. You don't have to put the 1 in front of the radical. And also when you divide the denominator by 2, you get 1. You don't have to write the 1 in the denominator. So this is how you would write the answer. If you look at the original problem again, you would not be able to divide by 2 right away because technically the number in front of the radical 20 is a 1. And 2 does not go into 1, even though 2 goes into 6. So you would not be able to simplify that from the beginning, but you could after you broke apart the radical 20. On number 6, the radical is already broken down for us. If you look at what's in common, we can divide them all by 4. And anytime the denominator is negative, I like to divide by a negative factor. So we're going to divide them all by -4. You don't have to do that, but you really shouldn't see the negative in the denominator. So -8 divided by -4 is +2. Plus or minus 4 divided by 4 is 1. Technically, when you divide this 4 right here by -4, +4 divided by -4 is -1. And then -4 divided by -4 is +1. Did I say that wrong? Positive divided by negative is negative. And then negative divided by negative is positive. So you still end up with one of each. Essentially, your plus or minus ends up flipping, but it's still 1 positive, 1 negative. 5 stays under the radical. And on the denominator, -4 divided by -4 is +1. You don't need to write a +1 in the denominator. Okay, a couple more of these. Just 2 more, just to make sure we understand this idea of simplifying, so that way it'll make tomorrow's lesson go a little easier. On number 7, you can divide them all by 5. That's all you can do there. Oops. You're going to divide by 5. 5 goes into all of those. The radical doesn't change, though. And then on number 8, kind of a trick question here. You can't break apart the radical 3. You're going to probably be really tempted to do the 24 divided by 6. But again, this radical 3 has a 1 in front of it, and 6 does not go into 1. Therefore, this is done again. You can't do anything with that. But what I see happening every year, no matter how many times I warn you, is -24 divided by 6. Students will write -4, and then plus or minus radical 3. They'll only end up dividing part of it by 6, not both. Okay, this is wrong. So 6 has to go into both terms to be able to do the division. So that was as far as that example goes. You can't do anything else with it. So we are done for today. Okay, your homework tonight is just to finish the same homework as the other night. Tomorrow you will have a quiz on solving by square roots. And then we're going to spend the rest of class tomorrow talking about the quadratic formula and also try to do a real-world quadratic formula example. See you guys then, or talk to you then.